which I'm showing here. And just to turn it around, you can see it's a complete model of the basic machine with different parts in different colors. For those who haven't seen the mini-mill, that is one of our club projects where we've got a working table down here which is about 400 by 300 and the height is about 250. And we've got a cross-axis running on these two rails here and a y-axis running actually on 3 rails in this direction and a vertical axis which runs on 2 rails. This is from a step files generated in solid edge that I converted and transferred into a finite element program, and then it was meshed with finite elements. And if you want to see the complete model, that's what the model looks like in terms of finite elements.
What program did you run it on?
The analysis is done with LS Dyna. Yeah, you can see the name here at the top. LS Dyna is a non-linear analysis program that I use on a daily basis in my work, so it's quite easy for me to do this. This is a very preliminary, what I would call a rough model. It runs, gives me an answer within about 5 minutes, so it's not a very comprehensive model, but it's got quite a lot of detail. If you look closely, you'll see it's got the slide blocks in here. It's got the rails with the correct shape in. There's a sliding interface here that these can actually slide in this direction. Only in this direction, it can't move in other direction. There's contact surfaces defined here. For each of them, here at the back, the same thing. The lead screws are a bit of just a single element, kind of an approach, very roughly made. But the main thing is here to get an idea of the performance of the machine in terms of when you apply forces here on the tool, what happens to the machine. So I've got sort of a couple of loading situations which I can run here on a time basis. First I put a force in this direction, in the lateral direction. I take it off and then I put a force in the rear, forward rear direction, and then I put a force in the vertical direction. And if I run it here on a time scale, you won't see any movement because the movements are so small that you can't see it with the eye. But I can change that with software, and I can increase the actual deformations by a factor, a scale factor. So this model is in millimeter. So if I put a factor of 1000 in here, then all the movements will increase by a factor of 1000. So what actually you see visually, 1 millimeter is actually 1 micron in real life. So it magnifies it so that we can see what it looks like. So if I now go through a cycle, you'll see some movements. See some movements through as I go through those 3-4 cycles, 3-4 cycles.
What force did you use, Prof?
I use 100 Newton.
100 Newton.
100 Newton, which is a sort of a typical cutting force for a 10 millimeter cutter, you know, running at a decent speed. It's sort of a design force, a basic design force, just to get an idea of what's going on. And
more blunt than that, it anyhow breaks.
Pardon?
The cutter, if it's more blunt than that,
yeah, there's a lot of parameters that plays a role, so you have to assume some cutting force.
100 apples, 4 apples per kilogram is 25 kgs.
Yeah. It's not a small force, it's quite a force. So the software allows you now to really have a look at it. If you look at it, say from the front, and you look closely, you'll see what happens, you know, how it moves. Remember, it's now magnified by a factor of 1000.
So how many millimeters of movement are you getting at that configuration?
I'm getting like 6 millimeters of movement now.
6 micron.
What you see, it looks like about 6 millimeters, which is 6 micron, 6 to 7 micron, with that cutting force. It's what we do now to balance it out. You know, if we see, that's one way of looking at it, but now to find out where it actually deforms, and you can see there's quite a bit of deformation in this area here. Let me just show you all the parts of the machine first. Let's go back and stop it so that you can see how the machine is built up. It's a number of parts. I can select. Software is a bit annoying part here. These are all the parts that have been modeled, so I can select. For instance, that's just the base, one casting, which weighs about 130 kilos. That's the base casting, which with the 3 tracks, there's a track there and another track here and another track here. And then these are just the linear rails. That's what I call the crosshead, which is in 2 plates. I'll show you in a minute. That's another rail. That's the block. That's another rail. That's the table. And that's the y-axis unit, which is quite a complicated casting as well. By the way, we've made about 4 or 5 sets of castings now, of which 2 have been accepted. The others were trials and were discarded. But I've got 2 sets. One machine has already been built and is being used, and the other one, we've got a set of castings that's now sitting and waiting to be machined. Just to complete it, that's the other plate. So these 2 plates go together. As you can see, they fit together. The yellow is actually a bad color. Let me try to improve the color there. You can see it better now. That's 2 plates that's bolted together. So it's easy to mount. You can actually take the whole head off and fix it up and set it up and then bolt it onto the cross. That's why we call it the crosshead, which is different in this particular version of the machine. And so on. Let me just see what else. These are blocks.
Prof, that's 2 plates just because for ease of assembly.
Ease of assembly. We found the initial prototype that we built at Eric Vosler is very difficult to assemble, and to get all the nuts to turn down. So I split that crosshead into 2 plates, so you can assemble the one on its own and the other one on its own, and then finally join.
And those 2 plates, you get dowel pins and screws, or how does it mount?
Yeah, it's got a locating pin, and then you can slide it on, and then you bolt it with a number of bolts. You can also now make adjustments. If there's something skew, you can set the verticality of it. You can check that and clock it up and set it.
That's quite interesting.
Most of the bigger machines are built like that. It's 2 separate items. I just wanted to show.
That cross plate is what material is that made of? That's not cast. That's steel, eh?
What is that?
The cross plates.
The cross plates will be steel, yeah.
Okay.
Well, we want maximum stiffness, so you can't do better than steel. You can do worse than steel. Cast iron is about 20% more flexible than steel.
Okay.
So we're working that. Where we need stiffness, we use steel. It's small plates that you just machine out of solid plate.
Are there any design changes you might make, having looked at the spinal element analysis on the stiffness? Then we want to change, or you think that's
okay? That's a good question. Let me just show you, and then I'll show you what I did. I wanted to show the Z-axis. Where is it? Here it is. Just this is the other casting, which is the vertical one. That's the vertical one, which has got its inside tracks here. Everything packed in here with a lead screw in the middle and the 2 tracks on the outside. That's the vertical one. And it's designed to take any kind of a spindle which you just bolt on the front here. Let me just switch off this, and makes it easier to see what it looks like. So the spindle bolts onto that. I've just modeled a very, very rough kind of a spindle here for testing purposes, which looks like that. So it's sort of what the current spindle looks like at the moment. Weighs about 7 kilos, such as 6 to 7 kilos. Design changes came into, the most difficult part is this interface between the vertical and the horizontal axis, and then between the horizontal axis and the base, those interfaces. And what I had to change, if I go back and show you everything, was over time come now. Oh, it's slow on the laptop. Yeah, you can see it here. I added another block here. I found that this part, and I've seen now, and I'll show you now what I mean. This part is still, I think I'm going to improve this in the next version. Going to fill that up, that angle a little bit, make it a bit stiffer there. There's a bit of rotation here, bending here in this area, but this putting these extra blocks in here helped tremendously to keep the verticality of the vertical axis, that it doesn't tilt when you push forward and backward. So that was one change. Otherwise, not much, just sort of getting the thicknesses right. And a difficult part to get stiff is this part here, especially from a torsional point of view, because it's an open profile. One can close it up like they do on bigger machines, but then then you can't fit any kind of a spindle onto it. Then you have to have a specific built-in spindle, and you can't change the spindle easily. Ideally would be to box it up. So I've increased the stiffnesses and the thicknesses here on this vertical axis to increase its torsional stiffness, and closed it up at the bottom and the top and so on. And I'm happy now with that. You'd be surprised, but the nuts and the lead screws themselves, they also have to select their sizes right. I've got 16mm lead screws in this, and I'm still not 100% sure that is sufficient. Maybe one should go in a little bit higher.
Rob? Yes, so I look at that model. How do you mount those two plates together? Have you got axis holes through the front in order to get to those screws?
Which plates?
Those two, yeah.
Yeah, it sticks out on the side. If you look carefully, you'll see there's a little bit of a face there.
Okay.
So the bolts are here on the outside,
okay, on
both sides. Yeah. In some places I actually have to get in and I actually have holes in the casting, so you can put a long Allen key through to tighten it up.
Okay.
Especially the nuts of the lead screws, those, to line them up, you normally have to turn it, move it a little bit right to the end, and then you tighten them, and then you can move it over the full length.
Okay.
But just to show you a little bit about, where's my full model now? Oops. To show you another way of looking at this, to look at deformation or stress, and we can switch on the stress. Where is it now? This program is a bit different to the one I normally use. Here it is. So, for instance, we can look at a stress value, like for Mesa stress is a typical stress value which gives you all over the picture of where the stresses are. You don't have to worry about the direction or anything like that. So if we plot it for Mesa stress, this is now before loading, so let me just load it up a bit. You'll see the colors develop. Let's just start this again. Stress. Something wrong with the coloring now. Stop. The graphic, this is a new program that I just downloaded, and the graphic seems to be a problem. What's it doing? There's something wrong with the graphics. Sorry, I didn't check that out. So I checked it out on another computer and it worked, but here on this particular laptop now it doesn't want to work. It's supposed to give me colors. Let's see if I can get something like this. Principal stress. There's some setup problem now. Sorry about that. But by plotting the stress values, when the stresses are high, you've got high deformation. So that immediately points you to a point where, if it's in the middle, where you can improve and increase the stiffness. We're not looking at local stresses, we're sort of looking at global stresses and deformations.
Now, have you got any idea of what these deflections that you're getting with the nose of the spindle, how they would compare with commercial machines? Have you got any figures and data to be able to make that comparison?
Yeah, but let me show you something else before we go there and discuss that. I can plot the values, rather than looking at these stresses. Let's see if we can plot. For instance, at the tip of the tool, I can plot the result of displacement, for instance, for a specific point on the nose. I picked it, I should just back to see. So I think, yeah. So I can plot, for instance, the lateral displacement and the forward-rearward displacement and the vertical displacement as a function. And for this particular system here, 12 means 12 micron. So when I move in the x direction, it moves 12 micron. Then I take the load off. Then I move in the y direction, and then there's no movement in the x direction, but there's movement in the y direction. The green is y, forward and backward. The red is lateral, the x direction, and the blue is the vertical direction. So using graphs like this, I can find out where the problem is, and this is still, as I said, I'm not finished with this. I've just started 2 days ago, and I have to work through this. But I just thought maybe tonight we can spend a bit of time to show you what's going on, how to do this. So ideally one would balance this so that in the x and the y direction you balance out that you get the same stiffness in all directions. The vertical stiffness, we normally want more stiffness, and it's easy to get vertical stiffness. But the lateral stiffness, especially on router type, this is a router type structure where you've got the bridge across and your slides on the sides, and typically a router is difficult to get lateral stiffness. And here we see it also, the red is a little bit more than the green, which is in the forward red.
The red, the X.
The red is the X, yeah. The red is the X.
I was just wondering, your main frame is open in the front.
Yes, yes.
And that's where your deflection is, on where you
exactly
showed us that.
Yeah.
Shouldn't it have a strap at the top?
That is but let me show you. That's an interesting question, or a comment. Let me show you. I can plot. In addition, let me just take it back. Now I must say this laptop is a bit slow. I can plot.
It's only about half a thou, 12 micron, yeah?
Yeah.
That's nothing.
See, there I've added now these blue. It should give me a list here, but these blue lines here are the deflections of the sides.
Yeah.
So by comparing points, various points on the structure, I can see where the weaknesses are. And this frame, even if it's open, is substantially stiff. We're getting like less than a micron deflection on the sides.
Prof, the thing that worries me, because I've been working small machines all my life, that's all I know. And your biggest problem is chatter.
Is?
Chatter. Harmonics.
Yeah.
Although you think you may be machining within 6 or 12 microns, you could pick up chatter. If you get the right harmonic frequency, you may pick up chatter. So the whole point is, what I've learned is, the more solid and stronger your machine is, the better.
Yeah,
otherwise, with certain speeds, it's going to start making a noise, and it's not going to cut smooth. Not because the system is your tool deflection, but it picks up a harmonic at a certain rate.
That's the next step. What we do with this same model, we do a harmonic analysis of the model.
So
we can do a vibration analysis of it. We get the natural frequencies of it. Then we check your cutting speed, your tip speed. Is that a natural frequency or not? We want to look move the frequencies up.
Yeah.
We can instead of using cast iron, we can use meionite. Meionite, the damping characteristics of meionite is like 25% better than cast iron. All those aspects we can use. We can put mass, not for stiffness only, but also for mass. Mass influences your frequency. So that's the beauty of this way. If you've got these tools, you can check all of that. You can actually simulate, move the tool, accelerate it, and see what happens.
Because the only other way I thought that you can get rid of this chatter is you must put a sensor on it, pick up the chatter, and then change your spindle.
No, we can model it. We can model it. We can simulate it and model it all in software. This is quite a fancy model in the sense that it includes all the linear guides. And if you look closely, let me magnify this if I can. Come on. Yeah, there we are. Let's have a look. We can see what happens here if I move it. Let me put the mesh on again because it makes it a little bit easier. Perhaps not. Let's see if we can see a movement there. Remember, this is now magnified 1,000 times. So you see this part is getting longer and shorter here. Let me switch the net on. You see the movement here, forward and backward. You see how it slides here.
That line is then on the wall screw then?
No, that linear guide is free to move forward and backward.
Yeah, but obviously if you move it from the front, you put it forcing that Y direction, that force then is on the ball screw.
Yeah, but there's only one ball screw and it's in the middle. So if you push it on the side, you can twist it. And that's the actual twisting that happens there. So that's how you find out whether your ball screw is stiff enough and whether your rotational stiffness is stiff enough, and if necessary, you improve that and you increase that.
So it's rotating on a vertical axis.
Yeah, let's plot it from the top, then you can see. You plot it from the top, you should be able to see what it looks like. Let me just stop it here. It's a bit slow, this laptop, to respond. There we are. Let's see if we can see now what happens. You see how it rotates?
Yeah.
One end goes up, the other one goes down. You see, it goes down, that goes up. And that's just because I'm pushing laterally here. There's a moment and it pushes laterally, so it pulls this side down and it pushes that side up. It pushes this side out a little bit as well. I mean, we can even make this factor bigger, make it 5,000. And you can even see more what's happening. Or 10,000, then we're working with see now, look at that. That's multiplied 5,000 times.
Would it make sense to have a bolt-in section on the front of the casting that you can bolt in, because the spindle doesn't come that far forward? I mean, if we had something in front bolted on with it as a one nice haunches on it, would that help to stiffen the frame?
The frame is not the problem. Most of the problems lie here in this area, and as you can see here in this area, that I think needs to be looked at. See, the linear guide only supplies lateral support. It does not give you any support in this direction. That all comes from the rear here. Now I've got a bit flexibility that I'm working on here at the back. I didn't model that very accurately.
So if you're cutting off on one edge and that you have the Y and you apply the Y on one edge, that's going to be quite severe. You're applying the Y almost on the linear guide now. Oh, sorry, on the lead screw now.
But the biggest problem is in this area at the moment. You can see here. You can see here, the biggest problem is here in this crosshead here. You see there how it moves.
Prof, these linear guides on your model, are they bolted on or are they solid? Have you got bolts in these linear guides?
No, I didn't model the bolts, so that's a bit of an
So the
assumption.
linear guide can actually still bend on itself.
It can
as
bend
well.
on itself, but it's in a groove. It's let into a groove. You know, it's really fairly solid into the casting. We cut that very accurately, and then we push them in, and then we bolt them down.
I've also heard of a factor called repeatability, where a machine is cutting and you tell it to make another one, and it must come back to exactly the same coordinates in terms of repeatability. But when you start stressing these materials,
No,
you get some memory and your repeatability is different.
no, stressing is so low. The stresses are less than in the order of 1 to 2 MPa, which is nothing in terms of the material. This material can take 200 to 250 MPa without any trouble. It's not a stress problem, it's a stiffness problem. Your repeatability comes in with your lead screws, your ball screws, and your linear guides, because those are sliding things. It's not bolted, you know, that's where your repeatability comes in. You get backlash or you get play in your ball screw, in your thrust bearing, in your nut, your ball nut. That's where you get the repeatability problem. You don't get it in the structure. The structure is never stressed to any extent.
Does that also imply that the oil you're using on your components, your ball screws, will affect?
Where you get stressing is, of course, between the ball and in everything that runs on ball bearings. You know, you get high stresses, but that's designed, you know, to take that, and it's hardened steel and so on. And you have to size those things that they are not overstressed. But in this case, we use 20 millimeter guides, which is a bit of an overkill. We could use 15 millimeter, but we've got 20 millimeter guides at the moment. So I'm not worried about that. And that's also a matter of fatigue and lifetime. In the end, if you use the machines like for 20 hours a day for many years, you may have a problem in your linear guides, but then you can replace them. They're not that expensive. You can replace them if you want to. But the material of the machine is never highly stressed. It's actually all over quite low stress levels. Well, I just thought it would be interesting to show you, you know, the kind of tools that we can use and how you can design a machine in terms of all your electronics and all your motors and all your stuff, but then you still have to design the structure as well. And if you haven't done that properly, then you haven't got, you know, then you have an unpredictable machine, unless you've got a good gut feeling about how stiff and so on. But I've seen many machines, especially routers, which are completely under-designed in certain directions, especially the lateral direction. You know, they just use a plate on each side, and the plate is easy to bend, and then you get vibrations and chattering and so on. Chattering is a problem, you know, for machining, and but we do a frequency analysis, and we try to get make sure that we haven't got a low frequency that can go into resonance. Yeah. But there's always. Pardon?
Cutters itself vibrate.
Yeah, the cutters, I mean, they vibrate on their own. You put a long cutter in, and you've got a 3-flute or a 2-flute cutter, you get vibration in the cutter.
Yeah. If you look at the surface of the thing you cut, it's like a third of a millimeter.
But there are so many parameters, your cutting speed, your feed speed, and so on, that you can change to reduce that.
Cutters, Prof, don't even have the teeth equally spaced around them. They have them, you know, if they have a 4-tooth cutter, sometimes they're not all 90 degrees apart. Just to stop that exact problem.
Exactly. The person who's now supposed to machine this new prototype for us has his cutters made so that you don't have a regular frequency, because he cuts so that you don't have to grind. He makes gears with complete finishing cut with the tools without any grinding whatsoever, and they use that gears just like that. And the key is, as you mentioned now, these special cutters I've seen them cutting 10 millimeter slots that deep with one cut. You can't feel vibration on the machine. And he showed me how special this cutter is made to do that kind of stuff. And the machine is heavy, as he mentioned. Heaviness is always an advantage. but it's a costly thing, you know. We can make it a ton if we want to, but we don't want a machine that weighs a ton if we can make it for, you know,
The other
for
thing is the
200
spindle,
kilos.
that can also turn not.
The thing with the machine,
Flywheel on it. That's
Yeah.
my question.
yeah, but if you make this heavier and thicker, you need a bigger motor. Everything goes up and up. Then you need a bigger drive. You need more current, you know, to move it, accelerate it, and so on.
But that deflection values for that, what I've seen here is actually for that, it says that design is very good. You know, the principle of the design.
Yeah. Now I'm happy with it. I've checked it. This is now a very preliminary model that I'm making now, just a final model. But I've checked it, and it's getting sort of 6 to 10 micron for 100 Newton. Now, you don't need to use 100 Newton. That's a big cut. A finishing cut is like 10 Newton or 20 Newton. So to get a better accuracy, you go for smaller cuts, a finishing cut.
We're making the classical fault now of finite element analysis, that magnification factor.
Yes. Now, when I show this to the clients, they go, oh, hell, this will never work, you know, look at that. And I tell them, well, it's magnified 5,000 times.
Prof, is there any news on getting those machines cut now, the castings?
Man, I'm at the point where I need to have a meeting and discuss that and see what's the way forward. We've waited long enough now. I'm sort of, this weekend or next week, I have to make a decision. If we can't get it done in a week or two, then I'm going to move to somebody else.
Have we got somebody else?
Not the same machinery, but it can also be done. You know, we have to compromise maybe a little bit, but I think it's worthwhile doing that. So I'm at the end of the line now for waiting, and we've got everything ready to go, but we haven't got machined castings. And I want to make new castings, but what I've done in the meantime, I've got the quotation to go to meonite instead of SG42. And to give you an idea, it's around about 80 Rand a kilogram instead of 55 Rand a kilogram. So it has advantages. It gives it's a denser cast. It's also a cast iron, but it's a very high quality, very well controlled cast iron. You have to have a license to be able to cast it. There are only 5 people in South Africa that can cast it. They've got the license to cast it. And it's more expensive, but the finish is better, and as I mentioned before, it's got better damping qualities. It's a harder material. Basically, Swiss and German machinery are done in meonite. And that's the kind of, you can drop an Allen key on it and there won't be a mark on it, whereas if you drop it in another kind of cast iron, you'll see a mark if you drop an Allen key on it too.
Yeah, but the main requirement for the meonite is the machining now, isn't it?
The machining has an advantage that you can use the same coolant apparently for meonite that you use for normal machining of other metals, whereas if you put cast iron in, you can't. It spoils the coolant and you have to replace the coolant, or you have to cut dry, and cutting dry, people don't really like to do that.
Yeah, so there is a cost complication there as well with having to replace the coolant, because that might make up the difference between the 55 and the 85.
Exactly, yeah. So in the end, the meonite may be a better option, and not that, it looks like it's expensive, but in the total it may not be more expensive.
It might cut down on the machining costs.
Yeah.
Would the German Deckel machines be done in meonite?
Pardon?
The German Deckel machines, would they have been done
Yes,
in meonite?
yes.
Ek het 'n vraagie, nee. Ek wil net weet, op tot hierdie stadium, wie finansier dit nou alles?
Ek en Ivan Moller finansier dit op die oomblik.
Okay.
Ons het wel geld gekry, maar ons wend nie eintlik die geld aan van sommige ons wat deposits, so ons het nog nie dit verwy nie.
Okay, so maar ek is nog nie op spoed nie, ons al op 'n stadium met 'n deposito betaal.
Sommige ouens het deposit betaal, jy weet dat paar ouens het regtig die ding gedruk in die begin, seker omtrent al 6 maande gelede, en hulle toen het deposit is neergesit wat nou nog daar lê en wag.
Okay.
Want die idee was ons so binne 2-3 maande so ons die goed begin gebruik het, maar dit het nou net nie so uitgewerk nie.
Maar sê maar net as daar
Geld is nie op die oomblik die opsie nie. Die opsie is om iemand te kry wat bereid is
wat dit kan doen.
wat dit kan doen, ja. Dis nie regtig 'n opsie nie. Die idee was net om eers 'n prototype klaar te kry en dan vir die ouens die ding te wys en te demonstreer en te sê, okay, nou as julle nou wil bestel, sit hulle geld neer, deposit toe, dan gaan ons aan. Maar dan is dit nog net nie daai punt bereik nie.
Is die probleem die masjien wat die job kan doen?
Ja, ja. Ja, die probleem met die masjien is dat hy nou, kom ek stop hom net hierso, vir die wat nou nie weet nie, hierdie is nou eintlik, kom ek wys 'n bietjie, hoe lyk die hele ding, kom ons gaan 'n bietjie uit die program uit. Julle nog 'n bietjie tyd, dan wys ek gou die wat nog nie gesien het nie. Hoe lyk die masjien?
Alweer.
Skoon tot ziens julle hoor.
Net 'n paar kies ek gou doen.
Nog iewers 'n banker of ons possie maak.
This is really the amendment 9.
En die goeders van Siemens af, prof, is daar enige sprake van delivery?
Ja, dis seker net so met hulle om dit. Hulle het gesê hulle gee dit vir ons en klaar, maar ek kry dit net nie. Ek vra hulle elke week en dan sê hulle weet nie presies wanneer dit kom. So dis ook 'n bietjie van 'n frustrasie. So ek net die hele masjien wys kry. Die laptop is bietjie stadig.
Heb je zo'n van die laptop?
Tot wat ze gebruiken. Die niet los straks.
Daar zijn. So dis 'n hele klomp parte wat daar is, daar selfs 'n Siemens controller op nou hier in die model. Maar dis is die masjien op die ou end veronderstel is om te lyk. Met controller langs die kant. Ons het 'n skenking gekry wat ons nou nog nie gekry het nie, maar ons is beloof ons gaan 'n Siemens controller kry en 3 motors om op die masjien te sit. So that's the overall picture. The machine is designed to get a 4th axis and a 5th axis into it. I'll show you in a minute. And these are the latest motors that I fitted onto it. Those are Heidenhain motors. There's some guys who says we want a Heidenhain control on it, not a Siemens control. So I just fitted the smallest Heidenhain motor that I can get with a brake onto it, and that's what it looks like. Okay, that's a tool changer spindle that can change. I have an automatic tool changer with it, so it's a bigger spindle with a separate spindle motor on top And just to show you also the other options, if you can find that. Difficult to see. Here's an extension to it with a 5-axis tilting table with a rotary table on it. Graphics, this machine is not very good. I don't use the laptop normally for this kind of stuff. I can't orientate it. Let me just try here. Something like that. The picking is not working very well. Anyway, you get the idea of this table. Just don't want to rotate something. So the table is tilted by this motor on the left-hand side, and this table is turned by a motor that sits in that underneath here. There's a flat motor that turns this table here. So that gives you then the 4th axis, this being this axis, and the 5th axis being this rotary table. So it can be a 5-axis machine in the end.
Your dimensions are about 500.
This distance here between the two walls is about 520. 520. The actual working area is 400 by 300 by 250.
So you need a truck company that's got a serious piece of machinery to cut that.
Yeah, that's what I wanted to show you, because we've got these things on the sides. Here we've got things fitting here. We've got some stuff fitting here on the back. We have to cut, horizontally and vertically around the machine. And we've got to cut the table at the bottom and so on the inside. And a big 5-axis machine is ideal, and we've got one here just 2 kilometers away from here with a 2.5 meter round rotary table and a 5-axis machine. You easily put it in the middle of this table and do all the cutting, and there's very little cutting to do on this casting, for instance, on the basic casting like I'm showing there. The cutting will take about 10 minutes and it's finished. It's more like drilling and tapping all the holes for the linear guides and so on. Very little machining to be done. The other way is to use 2 machines. You first do the vertical and then you take it off and you put it on a horizontal machine. And that takes time, of course, and another setup, which has to be accurate, clocking and so on to set it up. Whereas on one machine you can just plonk it down. The machine is automatic. It measures. You set your center and your height and so on, and it cuts. Everything is square, depending on the accuracy of that machine. And this machine is a Swiss machine that is got here. It's a very extremely accurate machine. So I'm still hoping that we will get it done there. It's just a matter of now trying to get it actually being done.
So you have to anticipate every single cut beforehand, because you can't take your machine back after 3 years, take it apart and machine another little flat somewhere. Because you have to plan this very well, so that the initial machining is everything. You're not going to go back.
Yeah, the idea is to use accurate machining, as accurate as possible, and just assemble. Fit in and bolt together, not to take apart, measure, clock again, scrape and file and so on, put it back and so on, not to go into that kind of assembly. The only thing that needs to be clocked up is the vertical, which use what do you call it? A stone, very accurately ground stone, angular stone to set up the head that it's vertical relative to the
That's almost a running adjustment more than that's a maintenance adjustment.
That's very easy. Just 4 bolts to loosen, shift and tighten again. But that's not the whole thing is to make it easy to assemble and to take it apart. If you have to change a micro switch or there's something wrong there, you can take it off and do that. Okay, I think that's it for the evening. Thanks very much. Thank you.
V10 minus V10.